So here we discuss second countability, and this is the content. First we define second countable spaces, then give some examples, and we will show that a second countability is stronger than first countability. And for that we will give some example of topological space which is first countable and not second countable. Then we prove two theorems that will generate more examples. Okay, and finally we discuss Lindelof and separable spaces. We define Lindelof and separable spaces and prove two theorems, and also we'll give some examples. So yeah, here we have the definition of second countable topological spaces. The definition is very simple. A topological space is called second countable if it has a countable basis. Okay, so before going to examples, we remark that second countability is stronger than first countability. That is, if a topological space X is second countable, then it is first countable too. Okay, to say this, let X be second countable with a countable base B. So we have assumed that X is second countable, and yeah, so as it is second countable, we have some countable basis B to show that X is first countable. Okay, for any point little x in that space X, we define B sub X equal to set of all basis elements in B that contains the point X. Okay, and of course this set Bx, this is a sub collection of a countable collection B, therefore this is also countable. So every subset of a countable set is countable. So this is Bx is subset of the countable set in this B. So Bx is countable, and of course this is a local basis of X at the point X, because if you take any if you take any open set O in X containing X, then because B is basis for the topology on X, we will get some element U from belongs to the set B containing X, such that U is contained in O. Okay, so because U is element in the basis B containing X, so U is in Bx also. So and we have U contained in O, therefore it proves that Bx is local basis at X. Therefore, yeah, Bx is countable basis of X at X. Therefore, X is first countable. Okay, therefore we conclude that X is second countable implies X is first countable. Now we give some examples. In the first example, we consider set of all reals. Okay, so we say that set of all reals with Euclidean topology, this is second countable. Okay, a countable basis of the Euclidean topology on R. So here on R we have Euclidean topology, and a countable basis of the Euclidean topology on R is given by the set of all open intervals a comma b, where a is less than b and a and b, they both are rational. Okay, so this is of course a basis for the Euclidean topology on R, and this is countable because set of all rational, so this is countable, therefore B is also countable. Okay, so B is countable basis for the Euclidean topology on R. Therefore R is second countable. And in general, for every natural number Rn, this is Euclidean space of dimension n, so this is Rn with equipped with Euclidean topology. This is also countable. A countable basis for the Euclidean topology on Rn is given by set of all products of intervals, okay, ai comma bi. This is interval ai comma bi product over I equal to 1 to n, okay. So n-fold product, this is open subset in Rn, and such kind of open subsets gives okay, so the set of all such open subsets gives a basis for the Euclidean topology on Rn. Here ai and bi, these are all rational numbers, and ai is less than bi for every I equal to 1 to n, okay. So this is countable because Q is countable, so this collection B, this is also countable, and this is countable basis for the Euclidean topology on Rn, okay. Therefore Rn equipped with Euclidean topology is second countable, okay. So in the third example, basically third example, this is non-example. So we have already seen that R omega, okay, this is R omega is countable product of real line R equipped with uniform topology, and see this is metrizable. So already we have seen in the previous lectures, this is metrizable, and therefore it is first countable because every metric space is first countable, so this is also first countable. So here we show that it is not second countable. So here in the previous slide we have remarked that x is countable implies x is first countable. So of course so we study the converse part, and in example 3 we show that x is first countable does not imply x is second countable. R omega, this is first countable because it is a metric space. We show that this is not second countable, okay. So here in this slide we prove that R omega is not second countable. The proof is by contradiction, and we use the following fact. The fact is, if x is second countable, that is if x has a countable basis script b, and A is a subspace of x with discrete topology, and subspace topology is discrete, then A is countable, okay. So this fact is quite easy to see. To see this fact for every, so suppose x is second countable with a countable basis b, and A is a subspace of x with discrete topology. To say that A is countable for every little a in A. So because A has a discrete topology, so a singleton set A, this is open in the subspace topology on A. Therefore we get some basis element denoted by UA, that is in script B, the basis countable basis of x, such that UA intersection with A, this is equal to singleton set, okay. Therefore the map from A to script B defined by small a that maps to UA. Okay, this is injective map. Okay, so we have a injective map from A to the script B, and B is countable, so therefore A is also countable. Okay, so we use this fact. Now consider the set of all sequences uh, in R omega. So set of all sequences in R omega with entries 0 and 1. So that is A equal to the set of all sequences xn, where n belongs to set of naturals, such that xn is either 0 or 1. So that is xn belongs to 2-point set, 2-point set 0 and 1. Okay, so this is well known that A is not countable, so A is uncountable. And you see, between the distance, the uniform distance between every two sequences x and y is 1 if they are different, that is x not equal to y. So therefore A has a discrete subspace topology. So, and this fact demands that A is countable, but A is not countable. Okay, so this contradicts the facts, therefore our omega is second countable. Okay, now we as we said, we prove two theorems. So in the first theorem, this is theorem 1, it says that subspace of a second countable space is also second countable. That is, if y is a subspace of x and x is second countable, then y is also second countable. Okay, so suppose x is second countable and y is subspace of x, then to show that y is also second countable. So as x is second countable, we have some countable basis. So suppose beta, so this is script B. So script B, suppose this is a countable basis for the topology of x. Okay, then we define B prime, script B prime equal to u intersection with y, where u belongs to u belongs to B. Then it is easy to see that this B prime, script B prime, this is also countable, because B is script B, this is countable. So corresponding to every element in B, we can have at most one element in B prime. So this implies that B prime is also countable, and of course this is a basis, okay, for the subspace topology on Y. So B prime, this is of course a basis for the subspace topology on Y. Therefore we have a countable basis beta B prime for the subspace topology on Y, and this proves that Y is also second countable. Okay, this is what we wanted to prove now. So here for every second countable topological spaces, its subspaces are also second countable. Here we can generate many examples. And the second theorem says that countable product of second countable spaces is second countable. Okay, countable product of second countable spaces is again second countable. That is, let xi be second countable with countable basis bi for every I belongs to a set of naturals. So that is, xi, this is countable collection of second countable topological spaces. So they have countable bases, let's say bi, this is countable basis of the topology second countable space xi, and x equal to, this is countable product of this countable collection. So this is product xi, where I runs through 1 to infinity. This is countable product. This is equipped with product topology. Okay, so this is equipped with product topology. So now we have x, now this is countable product, we equipped with product topology. So to prove x is second countable, okay, so to prove x is second countable, we only to construct a countable basis for the topology on x. So consider b, that is given by product of ui, where I equal to 1 to, here we have typo, this is infinite product of ui, where I equal to 1 to infinity. This should be infinity. Okay, this is countable product where ui belongs to bi for finitely many i's, and ui equal to xi for the rest of i's. Okay, and it is so an exercise prove that this is countable, b is countable, and of course this is a basis for the product topology on x, and that's why x is also second countable. This completes the proof. So some two things, so you have to check that this is countable and a basis for the product topology. That would complete the proof. Okay, so yeah. Now we define separable topological spaces. So first we define a dense subset. So suppose x is topological space and a is subset of the topological space x, then a is called dense in x if a closer equal to x. Okay, so this is a well-known definition. So I hope you have already seen this definition in your previous analysis course. Okay, so for example, a set of rationals, this is dense in set of reals. Okay, so q is dense in R, and set of irrationals, that is also dense in R. And for in general, for every n, qn set of rationals power n, that is Cartesian product of n copies of q, that is dense in n-dimensional Euclidean space Rn. Okay, so now a topological space X is called separable if it admits a countable dense subset. Okay, so for example, here you can see that R has countable dense subset, and that is Q set of rationals. This is countable and dense subset of R. So R is separable. Okay, yeah, this is, so R is an example of separable topological space. So here we prove that second countability implies separable. That is, in theorem 3, it says that suppose X is second countable, then there exists a countable dense subset of X. That is, X is second countable implies X is separable. Okay, so suppose X is second countable with countable basis given by script B equal to un, where n belongs to set of naturals. Okay, uh, so this is a countable basis of x. So we have to construct a countable dense subset of x. So we construct a by taking an element xn from each un. So that is a equal to the set xn, where n belongs to set of naturals, where and xn is element in un. Okay, and un for every n for every n natural. So un is an element in the countable basis. Okay, so from each basis element we take a point to construct the set A. Now one can say that closure of A equal to x, that is A is countable. So of course A is countable, and it is easy to see that A is dense in the topological space X. If you take some little x, a point in the topological space X, and any basis element un contained in the basis script B, and x belongs to un. That is, if you take any basis element containing a point x, then un intersection with A equal that is not equal to empty set, because xn is there. Xn belongs to un intersection with A, therefore un intersection with A, that is non-empty. That implies x is in the closure of A. That proves that A closure equal to the whole space X. That's why so we have a countable dense subset A of X that concludes that X is separable. Okay, that is, there exists a countable dense subset of X. This is the proof of theorem 3. Now we show so now first we prove theorem 4, then we define Lindel of space. Theorem 4 says that so if X is second countable topological space, then every open cover of X has a countable subcover. Okay, countable subcover. So so we prove that so here our assumption is, suppose X is second countable with, so as it is second countable, we have some countable basis. So we can take some countable basis of X, which is script B, that is equal to un, where n belongs to set of naturals. This is countable collection of open subset of X, and this is a basis for the topology on X. Okay, and let A be an open cover of X. So what to show? We have to show that the script A has a countable subcover. Okay, so we define J equal to set of all naturals. Okay, so set of all naturals such that Bn is, so better here we write better here we write un. Okay, so because B equal to un such that n contained in naturals. So set of all naturals n such that the nth basis element, that is un, so please replace bn by un. So un contained in some element an, some element of the open cover an. Okay, and C, then J is of course countable because this is a subset of naturals. So every subset of natural numbers, that is countable. So this is J is countable, and we define A prime equal to an belongs to the open cover script A such that n belongs to J, and this is un. Please replace this bn by un. So un contained in an. Okay, so the construction of J assures that there exists some u, so there exists some an in the open cover that contains the nth element un of the basis B. Okay, so then A prime, so corresponding to every element in J, we have an element an in A prime. So there exists some one-to-one correspondence between J and A prime. Therefore bijection, there is some bijection from J and A prime, and J is countable, so A prime is also countable. Okay, so A prime is countable as J is countable. Okay, now we claim that A prime is a covering of X. So it is enough to show that for any point little x in the topological space X, this implies X belongs to the union A, where A belongs to A prime. Okay, so that is X is subset of this union. So suppose X belongs to the topological space, little x belongs to the topological space X, then you see script A, this is cover of X. So therefore there exists an element A in script A such that X belongs to A. Okay, as this is covering of X. Now little x belongs to A, and A is open subset of X. Therefore there exists some basis element containing little x, that is there exists some un in the basis B that contains X, and un is contained in A. This is the definition of openness. Okay, so now you can see that this un is contained in A. Therefore there exists some basis element. So there exists some so for the basis element un, there exists some element in the open cover script A such that un is contained in A. Okay, therefore this n belongs to the set J, and for that element n in J we have an belongs to A prime. That's how we have constructed A prime. Okay, this assures that this small n belongs to J, and for this small n belongs to J we have an element an in A prime. That's how we have constructed A prime, and therefore un contained in an. This is the definition of A prime. Okay, an belongs to A for n belongs to J, and bn contained in an. So un contained in. So therefore we have X belongs to un, and that is the union contained in the union, because this A is a member of script A prime. So un is subset of this union. Okay, so we have started with x belongs to the topological space X and arrived at x belongs to this union, that is x belongs to topological space X implies x belongs to this union of A, where A belongs to script A prime. So that is what we wanted to prove. Okay, so if x is second countable, then every open cover of x has a countable subcover, and we define Lindel of space by following a topological space X is called Lindel of if every open cover of X has a countable subcover. Okay, so this is weaker than compactness. So for compactness, every open cover has finite subcover. So this is yeah, weaker property than compact spaces. Okay, now now we discuss an example before stop with this video. Consider RL with lower limit topology. This is basically set of all reals. This is the set of all reals is the underlying set, and her topology is generated by basic open sets like close the intervals close A open B where A is less than B and AB they are reals. Okay, so these are the basic open set that generate lower limit topology on R, and R equipped with lower limit topology we denote by R sub L. Okay, so here we show that every open cover of RL by basis elements, that is by basic open sets, has a countable subcover, and that would conclude RL is Lindelof. So basically to show every open cover of RL has countable subcover, it's enough to show that every open cover of RL by basic open sets has a countable subcover. Okay, so consider consider script A, that is collection of basic open sets A close A alpha comma open B alpha, where A alpha and B alpha they are reals, and A alpha is strictly less than B alpha. Alpha is from some index set, this lambda. Okay, this is a collection of basic open sets, and this is, suppose this is a cover of RL. Okay, so we prove that. So what we prove? We prove that this script A has a finite, has a countable subcover. Okay, covering RL. To extract a countable subcover of A, we define C equal to the open union of open intervals A alpha comma B alpha, so where alpha belongs to lambda. Okay, and now we claim R minus C, this is countable. Okay, R minus C, this is countable. So now see, now we analyze the set R minus C. If X belongs to R minus C, then X is not in the open interval A alpha comma B alpha. If X belongs to some open interval A alpha comma B alpha, then X is in the set C, but we have chosen X belongs to the complement of C. So X does not belong to open interval A alpha comma B alpha for every alpha in lambda. Okay, therefore this X must be equal to some A beta, because this is cover. Okay, so this is cover. uh, A is cover of R, so X belongs to R would imply X belongs to close alpha, A alpha open B alpha, so for some alpha, but we have seen that X is not in open A alpha comma B alpha for AB alpha, therefore X should be equal to A beta for some beta in the index set lambda. Fine. Okay, now choose a rational number denoted by Rx from the corresponding open interval A beta comma B beta. So if X equal to A beta, we choose some rational Rx from the corresponding open interval A beta comma B beta. Okay, then observe that if X and Y are 2 points in the complement of C in R, that is if X and Y are 2 points in R minus C with X is strictly less than Y, then Rx is strictly less than Ry. Okay, then we have an injective function from R minus C to Q defined by R maps to Rx. Okay, and this function depends on choice of Rx. Okay, so whatever Rx you choose, you will get X less than Y implies Rx less than Ry, and therefore this function X maps to Rx is injective. Okay, so if X not equal to Y, then one of them should be strictly less than another. So without loss of generality, X is less than Y, that would imply Rx is less than Ry, that is X not equal to Y implies Rx not equal to Ry. So this is injective. So Q is countable, so R minus C, this is also countable. Okay, and script A, this is open cover of R by open subsets. This is open cover, this is cover of R by open subsets, basic open subsets in the lower limit topology. So this is A is also okay. So A is also a cover of R minus C. Okay, now we can get, so and this is countable, so we can get some countable sub collection of A that is a cover of R minus C. Okay, so this is, so here we have proved that R minus C, this is countable. So we can get some countable subcollection A prime that covers R minus C. Basically for every for every a alpha in R minus C, we choose a alpha comma um, close a alpha comma open b alpha to construct the countable subcollection a prime. So corresponding to every element, we consider close a alpha open b alpha to construct countable subcollection a prime. Okay, that would cover R minus C. Now we consider C, where C is union of open intervals a alpha comma b alpha. This is C equal to union of a alpha comma b alpha, where alpha is from the index set lambda. Then you see so C is subset of R. Now consider the subset C with subspace topology of the Euclidean topology on R. Okay, so subset of, so, and you know R is second countable, and subspace of second countable space is also second countable. So therefore, if you consider subspace topology of the Euclidean topology on R, so with respect to subspace topology on C, C is second countable, and this is open cover a alpha comma b alpha. Alpha belongs to lambda. This is open cover, so this is open interval. So open intervals are open in Euclidean topology, and a alpha comma b alpha union over alpha belongs to lambda, that is exactly equal to C. So this is open cover, so open cover of C. So, and C is second countable, so it has a countable subcover. Let's say a alpha I comma b alpha I belongs to n. This is countable subcover of C. Now we consider a double prime. This is equal to set of all intervals, half open intervals, close a alpha I comma b sub alpha I. So corresponding to each element, we consider a close a alpha I comma open b alpha I, where I belongs to n. Okay, then this is countable collection. This is countable, basically sub collection of script A that covers C and A prime. This is countable sub collection that covers R minus C, and therefore the union A prime union with a double prime, this is union of two countable sets is again countable. And so this is, first of all, this is countable, and this is sub collection of script A and cover of R. So this first component covers R minus C, and second component covers C. So they all together covers R. So this is countable subcover. Okay, therefore RL is Lindel. Okay, that's it. Thank you.